In this video we're going to continue our look at using and evaluating conditional probabilities. So to begin with, let's just quickly recap the important probability rules. Probability A happens plus the probability A doesn't happen is equal to 1. The probability of A or B happening is equal to the probability of A plus the probability of B if the events A and B are exclusive. But more generally, the probability of A or B is the probability of A plus the probability of B minus the probability that both A and B occur. If we have independent events, then the probability of A and B is simply the probability of A times by the probability of B. But more generally, the multiplication rule for probabilities is the probability of A and B is the probability that A occurs times by the probability that B occurs given that A has occurred. The probability that B happens given that A has happened is the same thing as the probability of B and A happening divided by the probability of A happening. And the important thing with this formula is that we have to interpret what the event B and A really means. Okay, so let's move on to our first example. At a senior citizens club meeting, there are 8 men and 12 women. 2 of these people are picked at random. Find the probability that they are both of the same gender, and then find the probability they're both female given that the 2 people chosen are both of the same gender. Now part A could be done using a tree diagram. Equally well we can manage without a tree diagram if we're careful. So if we let M1 stand for the first person chosen is male and W1 being the first person chosen is female, and so we define M2 and W2 in a similar way, then the probability they're both the same gender is the probability we get a man first and then a man second, or we get a woman first and a woman second. Now, getting 2 men and getting 2 women are exclusive events. So we can certainly say the probability that we get 2 men or 2 women is the same thing as the probability that we get 2 men plus the probability that we get 2 women. Now in the original group we've got 20 people altogether, of whom 8 are men. So the probability the first one is a man is 8 over 20. If the first one is a man, then the probability the second one is also a man is going to be 7 over 19. And the multiplication rule for probabilities is going to tell me the probability of a man first and a man second is 8 over 20 times by 7 over 19. Similarly, the probability of getting a woman first and a woman second is going to be 12 out of 20 times by 11 over 19. And that simplifies to 47 over 95. For the second part of the question, we want to find out what's the probability they are both female given that the 2 people chosen are both the same gender. Now the words given that are really important in this question because it tells us we are after a conditional probability. So in part B, we need to use the rule for conditional probability. We want the probability they are both female given that they are both the same gender. So that from our rule for conditional probabilities tells me that I've got to work out the probability they are both female and both the same gender and divide it by the probability they are both the same gender. Now, if we stop and think about it for a moment or two, if I've got 2 people and I tell you they are both female and I tell you they are both the same gender, then you certainly know that the two people are definitely just both female. So we can simplify that statement of both female and both same gender into saying they are both female. So I've just got to work out, for my conditional probability, the probability they're both female and divide it by the probability they're both the same gender. We know the probability they are both the same gender is 47/95ths, and we know from our previous working that the probability they are both female is 12/20ths times 11/19ths. So my calculation is going to be 12/20ths times 11/19ths divided by 47/95ths, which ends up giving me 33/47ths. Moving on to our second example then, we have Andrew and Ian play a series of 3 games of pool. In each game, Andrew has probability 0.6 of winning and Ian has probability 0.4 of winning the game. And it may be assumed that the result of each game is independent of the results of the other games. We've got to calculate the probability of Andrew winning the series of games, and secondly, the probability that Ian won the first game of the last series, given that Andrew won the last series. So for part A, the probability of Andrew winning the series is the probability, first of all, that he wins all 3 games, or he wins the first 2 games and Ian wins the third game, or Andrew wins the first, Ian wins the second, and Andrew wins the third, or Ian wins the first, Andrew wins the second, Andrew wins the third. Probability that Andrew wins all 3 of the games is 0.6 times 0.6 times 0.6. That Andrew wins the first 2 games, Ian wins the third, is 0.6 times 0.6 times 0.4, because we've got independence of all of the games. Similarly for Andrew, Ian, Andrew is 0.6 times 0.4 times by 0.6, and for Ian, Andrew, Andrew is 0.4 times by 0.6 times by 0.6. So altogether here we've got 0.6 cubed plus 3 times 0.6 squared times by 0.4, which gives me 0.648. Now, for part B, we've got the probability that Ian won the first game of the last series, given that Andrew won the last series. So we've got a conditional probability again. So we're after the conditional probability that Ian wins the first game, given that Alan won the series. Now again, we need to use our rule for conditional probabilities. So that's the probability that Ian wins the first game and Alan won the series, divided by the probability that Alan won the series. Now, if Ian wins the first game and Alan won the whole series, the only way that can happen is for the series to go Ian, Alan, Alan. So we can say the probability that Ian wins the first game and Alan won the series is the same thing as the probability that Ian wins the first game, Alan wins the second game, Alan wins the third game. So our expression for the probability that Ian wins the first game, given that Alan won the series, becomes the fraction formed by, first of all, 0.4 times by 0.6 times by 0.6, divided by the probability that Alan won the series, which we know is 0.648. So our final answer is 0.144 divided by 0.648, which turns out to be 2/9. Moving on to our third example then, we have a medical test that's been designed to determine whether or not a random member of a country's population has or does not have a certain disease. At the time being considered, it's known that 2% of the population have the disease. The test is known to give a positive response showing that the disease is present in 96% of people who actually have the disease, but will also give a positive response in 1.5% of people who do not have the disease. So the first thing we've got to do is find the probability that a randomly chosen person taking the test gives a positive response. Now we could again do this by drawing a tree diagram, or we can do it by just trying to work our way through the possibilities. So we could get a positive response in two different ways. We could get a positive response by giving the test to a person who has the disease and then gives a positive response, or to a person who does not have the disease but gives a positive response. Now we know the probability that a randomly chosen person has the disease is 0.02. We know the probability then that that person gives a positive response is 0.96. So the probability the person has the disease and gives a positive response is 0.02 times by 0.96. The probability the person does not have the disease is 0.98, because 98% of the people don't have the disease. So we've got 0.98, but then if you don't have the disease, we're told that 1.5% of these people will give a positive response. So the probability that somebody doesn't have the disease and gives a positive response will be 0.98 times by 0.015. And altogether that gives me a probability of 0.0339 for the probability of obtaining a positive response from a randomly chosen member of the population. Now for part B, what we're being asked for, what's the probability that a person who gives a positive result has the disease? Now what we've got here is we want the probability that somebody has the disease given that, or if, they have had a positive result from the test. So we're after the probability that somebody has the disease given that we've had a positive result. So it's a conditional probability here. So using the rule for conditional probabilities, we can say that is the same thing as the probability the person has the disease and gives a positive result, divided by the probability that the person gives a positive result. From the working we've already done, we've got the probability that a person has the disease and gives a positive result is 0.2 times by 0.96. The probability that somebody gives a positive result is 0.0339. So the calculation we've got is 0.02 times 0.96 divided by 0.0339, which gives me 0.566. In other words, roughly 57% of the people who give a positive result have actually got the disease, and 43% of the people who give a positive result will actually have given a false positive. Now, obviously, a question like this has been really relevant over the course of the last year or so with the COVID virus. So just to finish this video off then, perhaps you'd like to have a look at these two examples, have a work through them, and then take your solutions in to your next lesson. And this video concludes our series of videos looking at conditional probabilities.